Hello everybody, welcome to today's session on the application of CNN in NLP domain. In previous session, we have already seen a couple of ways of modeling language in terms of RNN and its variant like LSTM. We have seen intra-attention, how they play between encoder and decoder. We have also seen inter-attention or the early concept of self-attention along with RNN. And today we are going to learn about CNN, how CNN can be used for sequence modeling. CNNs were introduced in 1990s. So although CNNs are known for image recognition, you can see the early popularization of CNN happened from a use case which was actually text. Of course, that was handwritten text, but it was text although. It is suitable for spatial data, not so much for the temporal data where you have a recurrent time component in place. Spatial data like image are more suitable for this. However, CNNs are extremely helpful for extracting feature, and we'll elaborate on this more on the subsequent slides. Just to motivate us why we are getting into CNN, let's see that the application of CNN is started long back. You will see that this paper was using CNN for sentence classification. Then you can see to 2027 there is a fantastic study done between the capabilities of CNN and RNN. A comparison was done between these two type of models, and what came out was that the RNN, while RNN will compute the weighted combination of all the historical words, all the sequence word, CNN can do a n-gram, which is the neighborhood, the word relationship between the neighborhood, and then do the activation. Okay, more on this point, we will understand this in detail. Then if you look at the very recent cases, like as recent as 2024, you will find some papers like LSTM CNN. They are still used for, let's say, understanding the fake news. This was published by one of this paper which is referred here. Similarly, and how it is done, you can see that they have used CNN, they have used bidirectional LSTM RNN, and then the fake news were detected in combination with this. So this is one of the trend which you still see, that because of its powerful capability of extracting feature, although a lot of advancement has happened on understanding the sequence model, CNN is still used, often in conjunction with the other model. So where CNN can perform better role and where other models which can understand the temporal information, for example here the LSTM is known for understanding the temporal information and CNN is known for the feature extraction. So they are combined to achieve very good score, like 98% you can see, to recognize the fake news. Similarly, you can see another paper which is also recent in 2020 to 2024. You can see that they have also constructed a CNN NLP model. This is especially used for meta-analysis from the research paper on medical term. So when it is not very natural language, but it is used for various types of medical knowledges or jargons, which are technical jargons, CNN can extract and understand those types of words very well. In fact, I have another video on this, which is about my thesis on open classification. There you can see that CNN has been used. In RNN, we are also doing the feature extraction essentially. Let's understand that. What do we mean? So see, the data are coming like this, one word at a time, and then finally we reach to from one stage to the tth time step. When we reach, we get that final summary HT, if you recall. That is a summary information of all the historical words or the sequences. This HT is nothing but a feature. This feature incorporates all the information which is there in its past data, in its historical data, as well as the current data. Okay, now let's move on to CNN and see that how CNN can be then applied for this one. In order to do so, we'll start with how CNN operates on the image itself. I have a video on this, which is not on this actually. That video was about understanding CNN network in terms of how many neurons are there in a CNN. So you can go back to the video if you want to develop more understanding on this. But let's have a quick recap and appreciate how CNN operates. Considering an image of 6 by 6 pixel. In reality, it could be 1024 into 1024 pixel or any other high density image. But for this purpose, let's say it's a 6 by 6 pixel and it has got 3 colors. That is what we call it as a channel. This could be any property of the image. Although here it is only color we have displayed, but that could be 10 or 20 types of properties of the image, which we call it as a channel. Now because it is a 2D image is a 2D matrix that way, therefore we apply a 2D convolution on this. Now see how convolution works here. It focuses, instead of going into 1:1 pixel, ideally that is how a feed-forward network will work. It will go to each point of the pixel. From one neuron it will have connection to all pixel, right? But the way CNN works, it will focus only on a particular patch, which we call it as a receptive field. So the neuron in this case has focused on a 2 by 2 patch, and therefore the size of the filter, we call it filter, we also call it kernel. So interchangeably we can use either kernel or filter, both are the same thing here. Kernel, that is why it is named as K1. This K1 kernel or filter has focused on 2 by 2 receptive field. After focusing this, a convolution operation will happen. What does it mean? It means that this has got 4 pixel, right? A, B, C, D, 4 pixel are there. And if the kernel size is 2 by 2 kernel, right? So if it is 2 by 2 kernel, then this also has equivalent amount of kernel elements, which is A, B, C, D, you can see. They will first do element wise product, okay, Ka multiplied by A, Kb multiplied by B, and so on, Kd multiplied by D. This is called the element wise product or the Hadamard product, and then this is summed up to give you a scalar value. That's the convolution operation. Now let's move ahead. The scalar value what we got after the convolution operation is stored in a place, and then the kernel moves up. It slides. This is called the stride, okay, and here it is stride without any overlap. You can also do, suppose the size instead of pace is 2, which is moving 2 pixel up instead of 8. If it is 1, then there would be 1 overlap. So the stride could be adjusted according to your need, how granular way you want to map the dependencies between the adjacent points and so on and so forth. So it has moved now 2 pixel up, and then it will do the same operation once again, and it will get one more scalar value which will be stored. Likewise, once we are able to slide through all the pixels of the image with a 2 by 2 kernel filter, we are essentially getting all the 9 scalar values for this. 1, 2, 3 this way, 1, 2, 3 this way, therefore we will get 3 by 3 matrix, right? What will be the size of this? There is a formula. Again, you can consult with my previous video where it has been explained how this is calculated. And then finally we can apply another filter on this. So per filter we try to capture one type of or one set of object there. For example, if this is a image of a human, and this is what is we are trying to capture eye, then the next kernel we can apply to capture something different. For example, this is going to capture the leg, and then this is going to capture another head. All of them will definitely going to give you similar feature map, and they are for different region of the picture or different element of the image they are going to capture. And at the end, I would also like to say that this feature map can be further downscaled by pooling mechanism, where it can take the maximum or the average of this value and then pass it to the next layer. That is how the images are learned in a convolutional neural network. Now let's see how it can be applied in a textual context or any sequence for that matter. So you see, the text is nothing but a vector, right? It's a one-dimensional vector. It's unlike image, that it is not a 2 by 2 or 1024 images. We have seen in our previous video, when you are doing embedding or one-hot encoding, you are getting a one-dimensional vector. So this is what is represented here. The first time step it has appeared. Now this is what you will consider this as a channel. It's one word and its dimension or the embedding dimension, it is the channel depth. And then we apply a kernel. In this case, we are going to apply a 1:1 kernel. The dimension should be, so it is going to focus only one. For example, there we are talking about pixel. Here it is going to focus only on one word vector. So it is therefore very similar to pointwise feed-forward neural network, because the neuron is connecting to each data point. Therefore, the kernel here has to match this dimension, because these are two vector now instead of two matrix. So we don't have to do a matrix Hadamard operation and then sum it up. It can be a simple dot product here, which will give me the scalar value. The next word will appear and similar operation will be done. The kernel will slide and then slide to the next word, and we get the next value, which is S2. And therefore, when we reach up to the tth step, we get the ST. We have represented this as a sequential operation, okay, just to comprehend the convolution operation, but in reality they are all done in parallel. As a result, in RNN, like we had to wait for the next word to appear, it only happens one at a time, then that leads to vanishing gradient problem. The recurrence also slows down the network. All this we had learned in our previous session. But you see, because convolution operation can be done parallelly, its time complexity of the sequential operation is constant, big O of 1. Okay, and then we already mentioned that since the kernel size is focusing only one word at a time or one vector at a time or one region at a time, this is equivalent to a pointwise feed-forward network. Therefore, the receptive field here is very narrow, unlike the image picture we had discussed, where we showed that one neuron is pointing to a region or a patch of the picture. That's how human sees. You don't see pixel by pixel, it sees a region. Therefore, it can map some kind of relation between one pixel to another pixel. In this case, we have, for a textual context, we are seeing that the kernel size is 1, therefore it is only pointing to one word at a time, and therefore its receptive field is very narrow. Maybe it can only map a adjacent word, but nothing beyond that, right? Here it is good for a fine-grained local dependency capturing, but not for global dependency capturing. How your first word and last word is correlated, it will have no capability to do that. That's how CNN is weak. At the same time, CNN is strong when it is doing parallel operation. In terms of computational complexity, you see this matrix is getting multiplied, so d dimension. Here also it is the d dimension, so that's why it is d raised to the power 2, d square, and you have this kernel. How many kernels getting applied? T number. There are t steps, so t number of kernels getting applied. Therefore, its computational complexity is big O of tk d square. Let's now see how do you then overcome this global dependency mapping. It is possible by doing so. Let's understand. Let's say now we represent these words in this manner, which is a 6 channel into t step, very similar to the previous one, but now we are thinking this as a kind of a matrix where this is one dimension is the channel, another is the t number of steps. And the first convolution operation has been performed, giving you the layer 1, the first feature map, right? All the scalar value after the convolution has been given. All this operation has been done parallelly, right? But they are pointwise. Receptive field is only local, the one. In the next layer, we are now stacking one more layer of convolution. So in the next layer, we increase the size of the kernel. Here it was 1, we double it. The receptive field is now increased from 1, right? Think about this, that now we are getting a global dependency mapping also. So here it captured a fine-grained feature. Here it is able to now understand how the two adjacent features are mapped. And in the next layer, likewise, in the next layer, once this will create a feature map, we can add one more stack of layer, which will increase from 2 to 4. And it is getting dilated, right? Every time we, instead of going into same size, we are dilating it by double the kernel size, and therefore it is able to map a bigger region. And till the end, when the entire picture has been mapped, okay, and then it is able to take the longer dependency as well. So in this architecture, what is happening, you can understand the number of layers is increasing. Therefore, the path length to map a dependency from word 1 to word t is getting longer. Okay, so that adds the additional computational operation. Since every layer the kernel size is getting doubled, so therefore there is a relationship between the number of layers and the total sequence length, which is nothing but exponential, because it is increasing, or it is doubling every layer. So the relationship is logarithmic, and the path length can be then given by this formula. The sequence has a logarithmic relationship with the kernel size k. So although here we are able to map the global dependency, it is still parallel operation, but the path length between any two word combination is increasing. It could have been also thought of a linear way of adding the layers. Instead of doubling the k, we could also add similar size of kernel 1, and keep on adding the layer. Still it is able to do the dependency mapping between the adjacent kernel, and we keep on adding such layers one after another, and in that case the number of layer will be t by k. Therefore in that case the the complexity of the path length, it is not the sequential operation, but the path length will be t by k. What about those complexities in RNN? In RNN, the sequential operation, we can understand that it is proportional to number of time steps. Very simple, right? Similarly, the path length. Your path length will also be same. We are just coming there. But the computational complexity is also d square, because there will be two metrics in this case as well, which is embedding dimension. Another is the hidden weight dimension d, right? Because of this matrix multiplication between two similar dimensional matrix, we will have the same d square as the operational computational complexity, and there are t such time step, so t into d square. Big O of t into d square is the compute. And like we said, that the maximum path length is also in this case t. Now we are going to do a quick summary of this. This table is a partial table from the paper of attention is all you need. In subsequent videos we'll learn transformer, and this is the comparison which will come up there, that why they have gone there, and that's why also this session, it's kind of a preparation towards the transformer. You can see that there is advantage when you are talking about number of sequential operation. CNN is constant, whereas RNN is depending on the number of steps. maximum path length also there is an advantage. This will be logarithmically coming down, but it is linear here. Okay. But when you go to the computational complexity, CNNs are more costly because there is an additional kernel factor here, where it is only dependent on the time step, but when you perform CNN on them, you are including the additional kernel factor here. So it is more costly for a similar operation. Now we are going to touch upon a simple piece of code, although we are not going to build the entire CNN based model. Not so relevant at this moment. Later on during the course of our learning, if that requirement comes up, we'll develop a model using that. But as of now, we are just going to prove this, that how convolution operation is actually essentially a dot product. So that's the small piece of code we are going to show it to you. Here we have created a dummy word embedding of this size, which is there a number of words are 4. And we have taken each word size as 10. This number of step we have taken as 4, and this dimension here we have taken as 10. So after initializing a random word embedding, you can see these are our vectors. So coming here, you can just see that this is a model we have created using a conv1d. It is a one-dimensional vector. Therefore, we apply a conv1d operation on a sequence data. Filter is 1, kernel size is 1, that is how you apply the kernel size. Okay, and then in the output, once the model is initialized, we give the word embedding. Only thing, we add the batch dimension here, because TensorFlow will expect the data to be given as batch. In this particular case, the batch size is 1. I am going to set this to none, which means it's flexible. After that, once this output is passed, we get the output as these 4 values. There were 4 sequences, number of words is 4, therefore we got here 4 outputs here. Each one of them has given a scalar number. Okay, we are going to now perform this manually and then see inside the convolution operation what is exactly going on. So we get the model weight first. You see there are weight and one bias. So the 2 output it has given, one is weights, another is bias, W and P. So we take the weight, which is of this dimension, and this is the bias. So our interest is only on the weight. So we take the weight as a filter. The filter is nothing but a weight. That is what is the thing which you need to note here. And the kernel size or the filter size or the weight matrix here is of the similar dimension of the embedding. You can see here. That's what we showed in this line. The dimension is 1, right? Okay. And then what we are going to do is the same operation. Manual convolution output is nothing but a dot operation, np.dot product between the word embedding and the filter. Between the word embedding and the filter, we did a dot operation to get this scalar value. Between the word embedding and the filter is transposed so that the dot operation can be performed by shape, and then we get this output here. Let's see whether we have matched here. The first one is 1854. Let's remember 18. Then the second one is 17, third one is 13, fourth one is 58. Let's see the output. 180. So 0, second one didn't match. Then the 13 and the 58. All of them are matched except the second one. Why not? Because we applied a activation here, ReLU. And the nature of ReLU function, you know that whenever it is less than 0, it will make it as 0, right? So that was the, so if we apply ReLU now, which is nothing but maximum, np.maximum you take. If you do that way, then the output matches here. 185418. This is now become 0 because it is negative value. So it will make it as 0. And then 13 and then 58. All the values are now matched. So that was the small piece of code to give you confidence that in a sequential operation per word, and the kernel is essentially getting dot product. Okay, we are also having a video on the essence of dot product on the machine learning, so please watch that video as well. So in this video, what we learned is that CNN, although they are predominant in the field of image analysis, can be applied to sequence modeling, considering each sequence as a one-dimensional vector. Therefore, a 1D convolution can be applied on all of them, and then it has got certain advantage and certain disadvantage. The advantage is that it can do a parallel operation, unlike the RNN model where the sequence becomes a bottleneck. CNN can perform very well. However, the problem with CNN is that it is more aligned with local dependency capturing. So for fine-grained information capturing, this works well. Possibly when you are talking about a small text like tweet or like a small Facebook post, medical term or jargons, there CNN plays a very important role, possibly better than what RNN can do, and in a very less expensive way, much faster, parallel way. However, when we are trying to do a language model which deals with a large text, for example, machine translation or document summarization, for those cases, RNN is the better choice because it can learn global dependency mapping. So our problem is more of a longer sequence handling. As we move ahead, we will see that the problem boils down to how do we increase the length of the input sequence, okay? Given the constraint of various computational factor and the path and those three complexity what we discussed. Okay, so this is all about this video. See you in the next video.